Okay, so what I'm going to try doing now is the last tool that we need before we can actually start using Laplace for very interesting things like solving differential equations set up as a linear system of equations. And to do that, all we need to do is look at the final Laplace transform of the derivative functions. So things like the first derivative of f prime t, f double prime t, f triple prime t, as such. And just to give you a heads up, that the algebra is extremely, extremely easy and extremely easy to get wrong. It's very, very fiddly. And I've got it wrong nearly every single time just by carelessness. So it's you'll probably do it a lot better than me, but just a brief warning. So let's just dive in and have a look at the functions that we need to look at. So what we want to do is find the Laplace transform of f prime t. Okay, so that's the first derivative of t. Yeah. So as we know by now, that's going to be the semi-infinite integral evaluated at the positive infinity and 0 limit of the function. Well, in this case, the function is f prime t e to the minus st dt. Yeah. So as you can see here, using integration by parts is going to be the best way to do this, because we can just use this as the part that we're going to integrate to get back to f of t, and everything should simplify to something much nicer. So let's see, v du equals uv minus v du u dv. Okay, and what we're going to do is we'll set, say, v and du, we want du to equal f of t. Sorry, f prime t. And then we can say that u, or the integrator of that, the integrand of that is just going to be f of t, isn't it? That's nice and straightforward. And we'll have dv over here. And then v is just going to be e to the minus st with respect to t. So if we differentiate that again with respect to t, we'll get minus s e to the minus st. Yeah? So let's rewrite that and say this equals uv, which is f of t e to the minus st. Yeah? And that's obviously evaluated at the limits. Minus u, which is f of t, dv, which is minus s e to the minus st dt. Yeah, and that's evaluated again between positive infinity and 0. So let's simplify this over here. We can bring this down. So that's going to equal f of t e to the minus st, evaluated between positive infinity and 0. Now we've got a minus here, and we've got a minus over there as well. You can see that. And I'm going to bring the s out, because remember, the s is just a constant here, yeah? Because this whole integrator is with respect to t, so everything else, all the other variables are just going to be constants. So I can bring the s out, and I can change the double negative to a positive. So I can say plus s between positive infinity and 0, f of t e to the minus st dt. Yeah? So that's nice and straightforward. Now, the bit we have to think about here is what's this going to evaluate to? So let's think about this. If this part here, e to the minus st, well, we know what e to the minus st is going to look like. It's going to look something like this. It's going to look something like this, which is going to go to, which is going to tend to 0 as t tends to infinity. Yeah? The only problem is that we've got another function here that we're multiplying it by, f of t. Now let's say that for f of t, as t tends to infinity, f of t is going to tend to something larger than 0. Let's say it's going to tend to a non-zero number. It might tend to a positive number. The product of those two functions are what we're interested in. We're interested in the limit of the product of these two functions. So it could actually very well be that this does not tend to 0. However, do you remember at the very, very beginning we said that a condition of Laplace transforms is that the s, the magnitude of s, is large enough over here for this function such that the product of this function and this function when t tends to infinity is 0. That's a very, very important point. So we can say that as t tends to infinity, the product of f of t in e to the minus st is indeed going to tend to 0. Why? Because the magnitude of s is going to be sufficiently large. Okay? If it wasn't, then we couldn't guarantee that the product of those two functions is going to tend to 0 as t tends to infinity. But since that's a primal condition of the Laplace transform, the primal assumption, we can assume that as f of t, as t tends to infinity, the product of those two functions will indeed tend to 0. So I just wanted to elaborate on that a little bit. I hope that was clear. So there you go. So as t tends to infinity, the product of those two functions is actually going to tend to 0. So we can say that's going to be 0 minus e to the minus s0. Well, that's e to the minus 0. That's 1. So that's 1 times f of 0. 1 times f of 0 is just going to be f of 0, whatever that is. That might be 1, 2, 3, whatever. You know? So it's going to be 0 minus f of 0. That's the first part evaluated. And then we're going to do plus s. Now, does this look familiar? The semi-infinite integral of f of t e to the minus st dt? Well, it should be, because that is just the Laplace transform of f of t, isn't it? We know that. So, we can say that the Laplace transform of f prime t, the first derivative of f of t, is in fact just going to be minus f of 0 plus s times the Laplace transform of f of t. And do you remember that we said that the Laplace transform of f of t is denoted as f of s? We said that before. So we can actually say that the Laplace transform of the first derivative of the function is going to be minus f of 0 plus s f of s. And there we go. Now, you know what, I'm going to put this in the box as well. See why in a minute. Now, we've just worked out the Laplace transform of the first derivative. Now let's look at the Laplace transform of the second derivative. I'm going to move that up so we've got a bit of room. So now let's say the Laplace transform of f double prime t is going to equal, well, what I'm going to do, I'm going to replace prime t, f prime t, over here in this box, with f double prime t. So we've got f double prime t equals minus f prime 0 plus s of the Laplace transform of f prime t. Yeah? Did you follow that from here? I just replaced f of t with f prime t, and therefore f prime t is going to be f double prime t. Yeah? So we've got the Laplace transform of f double prime t is going to equal minus f prime naught plus s of the Laplace transform of f prime t. But we know what the Laplace transform of f prime t is because we've just worked it out over here, haven't we? So let's substitute this into here. So I'm just going to rewrite this as the Laplace transform of f double prime t equals minus f prime naught plus s, a large bracket over here, and I'm going to replace f prime t, sorry, the Laplace transform of f prime t with the Laplace transform of f prime t, what we worked out over here. And that's just going to be minus, you know, I'll do that in a different color, minus f naught over here, plus s, f of s. I'm going to leave f of s as the Laplace transform of f of t over here, okay? Just for simplicity. Now let's simplify that. So we can say that that is going to equal minus f prime naught minus s f of naught plus s squared times the Laplace transform of f of t. This is where you need to be very, 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 very careful, just with the algebra. Very easy, but it's very easy to muck it up, and I've done it several times. So we can, and then say that this is, yeah, this is going to be the Laplace transform of f double prime t, the second derivative, yeah? Now let's have a look at the third derivative. So all I'm going to do, I'm going to move this up again. That's a bit more room. So the third derivative, we can say that the Laplace transform of f triple prime t is going to equal, again, I'm just replacing f double prime t with triple prime t and f of t with f prime t, yeah? So f triple prime t equals minus f double prime naught minus s f prime naught plus s squared times the Laplace transform of f of t. No, it's not going to be the Laplace transform. It's going to be the Laplace transform of, the Laplace transform of f prime t, isn't it? Yep. And we know what the Laplace transform of f prime t is. So let's substitute. So we've got minus f double prime naught minus s f prime naught plus s squared times the Laplace transform of f prime t. Let me go back down so you can see f prime t. There we go. So we can see here f prime t is minus f naught plus s f of s. So let's just replace that again. And again, I'm going to do that in red to make it clear. Minus f of naught plus s plus transform of f t. Okay, or you could just say f of s. So let's substitute this and simplify rather. Minus f double prime naught minus s f prime naught minus s squared f naught plus s cubed times the Laplace transform of f of t. So we can say, therefore, that the Laplace transform of f triple prime t is going to equal minus f double prime naught minus s f prime naught minus s squared f naught plus s cubed f of s. Okay, so I'm going to go to another page. Okay, so what I'm just going to copy out the results that we had. So we've got them one underneath each other. So there's a pattern that's starting to emerge here. Now, what I'm going to do is actually just rewrite this. But I'm going to replace the Laplace transform of f of t with f of s. So we can say that the Laplace transform of f of t equals f of s. That we know. And the Laplace transform of f prime t equals s f of s minus f naught. I'm also going to rearrange the order in the descending powers of s. And then we can say that the Laplace transform of f double prime t, this one over here, is s squared f of s minus s f naught minus f prime naught. Yep. Now let's do the same for the third derivative, the Laplace transform of f triple prime t equals s cubed. See that? The s cubed f of s minus s squared f of naught minus s f prime naught minus f double prime naught. So we can see what's starting to happen here. Let's have a look at this. So we've got Laplace transform of f of t is just f of s by notation or definition. Laplace transform of f prime t, s f of s minus f naught, double prime t, s squared f of s minus s f naught minus f prime naught, and f triple prime t, we've got s cubed f of s minus s squared f of naught minus f s f prime naught minus f double prime naught. Now, what I'm going to do next is introduce some notation to make this a lot easier to write down. So if we say that f of s equals x bar, yeah, which is obviously the Laplace transform of f of t, and what I'm going to do is introduce another notation here. Let's see. If we do this f of naught as, say, x naught equals f of naught, and x1 equals f prime naught, and x2 equals f double prime naught, and x3 equals f triple prime naught. If we introduce this notation, let's rewrite these equations. And what you should start to notice is that we're now starting to form a linear, and this is where the magic really comes in, a linear system of equations to represent a nonlinear system of differential equations. So let's proceed. So we can now say that the Laplace transform of f of t equals f of s, for the x bar, and the Laplace transform of f prime t now equals s x bar minus x naught, yep, because x naught equals f of the function evaluated at 0. Let's carry on. Now the Laplace transform of f double prime t is equal to s squared f of s, or that's x bar, minus s f naught, or f naught is x naught, minus f prime naught, or f prime naught is x1. Yep. Now let's do the Laplace transform of f triple prime t. That's going to be s cubed x bar minus s squared x naught minus s x1 minus x2. Yeah. Now let's see what we think is going to happen. We can actually start to notice a pattern here. So I'm just going to move the paper up so you can get an idea of where I'm going to be going with this. So now we can say that the Laplace transform of the fourth derivative, and another thing that we can do as well, we can actually replace this notation here with f of t equals x, f prime t equals x dot, and such. So you know what? Let's do that. The Laplace transform of f 1, 2, 3, 4 dots, just like that. We can do that. Is going to equal s to the 4 x bar minus, you see you've got descending powers of s here, s3, 2, 1, 0, s to the 4 minus s to the power of 3 x 0 minus s squared x1 minus s x2 minus x3. Let's go to the fifth derivative, x dot 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 dot. The fifth derivative of the fifth derivative is now going to be s to the power of 5 x bar minus s to the 4 x 0 minus s to the 3 x1 minus s squared x2 minus s x3 minus x4. So now just let's rewrite that very quickly in terms of a full simplified notation. And then we have all the Laplace transforms for the derivative functions from the first derivative to the fifth derivative, set up as a linear system of equations. So you can see that you can see how powerful what this is going to enable us to do. In the next video, I'm going to be using this result to start solving differential equations set up as a linear system of equations using this method. So I hope you enjoy.